Galaxies grow according to a hidden cosmic blueprint, one written into the fabric of reality itself. We will explore the architects of infinity, the hidden patterns that dictate the birth, life, and death of every galaxy. By the end, you will understand the secret forces that designed our universe and how they continue to shape it today. What if the elegant spiral of a galaxy is not a random shape, but the result of a precise mathematical rule? Could the invisible hand of dark matter be the true sculptor of these cosmic islands? This journey uncovers the blueprints that have guided galactic growth for billions of years. What does it mean to live in a universe that follows a grand design? This cosmic blueprint began with the faintest of whispers. In the earliest moments, the universe was not perfectly smooth. It held tiny, almost imperceptible ripples in density, regions where matter was ever so slightly more packed together. These minute fluctuations were the seeds from which all structure would grow. Think of a perfectly still pond. If you gently tap the surface, a series of ripples will spread out. Those initial ripples are the fluctuations, and the vast, interconnected structures they create are the galaxies and clusters we see. In the cosmos, gravity acted as the amplifier. A region with just a little more mass exerted a slightly stronger gravitational pull, drawing in more and more matter from its surroundings. Over billions of years, this process of gravitational instability caused those tiny overdensities to collapse in on themselves, forging the first vast clouds of gas, the protogalactic clouds that were the cradles for the very first stars. Cosmologist Margaret Geller's work helped us visualize this, showing us that the universe's large-scale structure resembles a cosmic web, a tapestry of immense filaments and vast, empty voids. But where did those initial ripples, those seeds of all structure, come from? The answer is written in the oldest light we can see. The cosmic microwave background radiation is a fossilized glow from the infant universe, and when we map its subtle temperature variations, we are essentially looking at a baby picture of those density fluctuations. The patterns we see are not random. They reveal a startling preordained framework, a precise set of instructions for how gravity would later weave the cosmos. This delicate balance between the chaos of random fluctuations and the unwavering order of gravitational physics set the entire stage. It raises a profound question. If the seeds were planted so long ago, what specific forces then took over to sculpt individual galaxies from those primordial clouds? That baby picture of the universe held the seeds, but it did not reveal the final forms. From that primordial chaos, gravity began to sculpt distinct galactic architectures, and none is more breathtaking than the spiral. Its graceful arms, swirling out from a brilliant core, seem to embody cosmic order itself. Yet this beautiful pattern is not a fixed structure like a frozen whirlpool. It is a dynamic, ever-changing phenomenon, a symphony of motion and matter playing out across billions of years. The secret to the spiral galaxy lies in a concept known as a density wave. Imagine a traffic jam on a circular highway. The jam itself is a region of high density, but the individual cars are always moving into it, slowing down, and then eventually moving out the other side. The jam persists as a pattern, even though the cars composing it are constantly changing. In a spiral galaxy, the spiral arms are the traffic jams. They are waves of compressed gas and dust that sweep through the galactic disk. As clouds of interstellar gas enter this wave, they are squeezed. This compression triggers the collapse of these clouds, igniting the birth of brilliant, short-lived, massive stars. These hot, blue stars light up the arms, making the spiral pattern visible. The stars themselves do not stay locked in the arms forever. They orbit the galactic center, passing into and out of these density waves over millions of years. This elegant theory, pioneered by astronomers like Lin and Xu, explains why spiral arms can persist for so long without winding up into a tight, indistinguishable not due to the galaxy's differential rotation. We can see this grand mechanism at work in stunning clarity when we look at the Whirlpool galaxy. Its perfect spiral form is not just a solitary masterpiece. A smaller companion galaxy is performing a gravitational dance with it, its tidal forces acting like a steady drumbeat that excites and sustains the density wave, keeping the spiral arms sharp and well-defined. This reveals that these patterns are responsive, shaped by both internal dynamics and external interactions. Yet, for such a delicate pattern to remain stable across cosmic time, there must be an invisible anchor, a steadying hand that prevents the entire disk from flying apart. This leads our gaze to the profound and unseen influence of the dark matter halo, a gravitational scaffold that holds the entire luminous galaxy within its embrace. That invisible anchor, the dark matter halo, is the true foundation of every galaxy we see. While the luminous stars and gas trace out beautiful spirals, they represent only a small fraction of the total mass. The rest, the overwhelming majority, is this mysterious, unseen substance that forms a vast, spherical scaffold extending far beyond the visible galactic edge. This dark matter halo provides the essential gravitational glue. Without its immense, steadying pull, a galaxy like our own Milky Way would simply tear itself apart. The stars in the outer regions orbit at such tremendous speeds that the centrifugal force would fling them into the intergalactic void, like riders on a merry-go-round that has spun out of control. This was the pivotal discovery made by astronomer Vera Rubin. She meticulously mapped the rotation curves of galaxies, expecting to find that stars farther from the center moved more slowly, just as planets farther from the Sun do. But the data revealed something astonishing. The orbital speeds remained high and flat all the way to the visible edge, defying the laws of gravity as we understood them. The only plausible explanation was that an enormous halo of invisible mass was enveloping each galaxy, its gravity holding the entire structure together. This hidden architecture is not a passive framework. Sophisticated computer simulations, like the Illustris TNG project, show us how the properties of a dark matter halo directly dictate the fate of the galaxy it hosts. The halo's total mass determines how much ordinary, baryonic matter it can gather. Its own internal dynamics and merger history decide whether that collected matter will settle into an orderly spiral disk or a featureless elliptical blob. These digital universes reveal a cosmos where dark matter acts as the master sculptor, channeling gas and dust into specific, stable configurations according to a set of hidden rules. Yet, this relationship is not entirely one-sided. From the very heart of these galactic formations, another force emerges, one capable of pushing back against the inflow of matter. Lurking at the center of nearly every large galaxy is a supermassive black hole, an entity whose violent outbursts can shape its entire cosmic neighborhood, creating a feedback loop that speaks to a deeper level of cosmic engineering. But the growth of a galaxy is not a peaceful, solitary affair. From the very beginning, the cosmos has been a stage for a more violent form of creation, a process of galactic cannibalism that follows its own ruthless pattern. Galaxies grow not just by gently gathering gas, but by consuming their neighbors in a hierarchical sequence of mergers. This is a fundamental rule of cosmic construction. Small protogalactic fragments collide and merge to form larger galaxies, which then, over billions of years, continue to devour smaller companions or engage in titanic clashes with their equals. These interactions are not random acts of destruction. They are a regulated, predictable process that forges new galactic architectures according to a strict set of gravitational laws. We can witness this process in its different stages. A minor merger, where a small dwarf galaxy is swallowed by a large spiral like our Milky Way, is a relatively gentle affair. It slowly donates its stars and gas, adding to the larger galaxy's halo and subtly thickening its disk. But a major merger, when two spiral galaxies of comparable size collide, is a cosmic cataclysm of an entirely different order. The delicate gravitational ballet that maintains their spiral arms is violently disrupted. Their clouds of gas are slammed together with immense force, triggering an explosive wave of new star formation known as a starburst. In this frenzy, billions of stars are born in a short, brilliant flash. The beautiful spiral structures are utterly shredded, and the resulting galaxy, after the chaos settles, is often left as a smooth, featureless elliptical blob. This transformative process is our own galaxy's ultimate fate. The Andromeda galaxy is hurtling towards us, and in about 4.5 billion years, the Milky Way and Andromeda will meet. Computer simulations of this epic collision show a breathtaking dance. The two galaxies will first pass through each other, their mutual gravity stretching them into long, luminous streams of stars called tidal tails. They will then swing back, merging their cores over multiple passes to form a single, enormous new galaxy, most likely a giant elliptical. Astronomers have given this future entity a name, Drumda. The evidence of such past cannibalism is written across the sky for those who know how to look. Pioneers like Alar Tumor showed that the remnants of mergers often bear distinct fossil records. You can find vast, faint shell structures of stars wrapped around an elliptical galaxy, like the ripples from a stone thrown into a pond, marking the rhythmic settling of stars from a devoured companion. Those spectacular tidal tails, arcing through space, are the temporary graves of the spiral arms that were once there. This relentless cycle of construction and destruction, of galaxies building themselves through a series of regulated mergers, points to a deeper level of organization. It suggests that the growth of galaxies is not a free-for-all, but a process channeled by the larger cosmic environment. This leads us to the grandest pattern of all, the cosmic web, the underlying architecture that orchestrates this entire hierarchical dance from the very beginning. This relentless cycle of construction and destruction is not playing out on a featureless stage. The galaxies we see, from the isolated spirals to the bustling clusters, are all strung along a single, breathtaking structure, a cosmic web that stretches across the entirety of the observable universe. This is the ultimate blueprint, a pattern so vast it makes individual galaxies seem like mere points of dew on an invisible spider's silk. The distribution of galaxies is not a random scattering. Instead, they trace out immense filaments, long, winding rivers of dark matter and galaxies that can stretch for hundreds of millions of light years. These filaments connect at dense nodes, which are the great city centers of the cosmos, the galaxy clusters where thousands of galaxies swarm together. And between these luminous structures lie the voids, incomprehensibly vast regions of near emptiness that make up most of the universe's volume. This entire cosmic architecture, this sponge-like structure, was already encoded in those primordial density fluctuations from the universe's first moments. The slightly denser regions became the seeds for the filaments and nodes, while the underdense regions expanded into the great voids. Dark matter forms the skeleton of this web. Its gravitational pull is what first defined these pathways. Ordinary gas, the raw material for stars, then flows along these dark matter highways, funneled by gravity toward the intersections of the filaments. It is at these cosmic crossroads that the most massive galaxy clusters are built, fed by a continuous stream of material flowing in from all directions. We can now see this blueprint directly. Massive redshift surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have painstakingly mapped the positions of millions of galaxies. When you plot them in 3 dimensions, the result is not a random cloud of points. It is an intricate cosmic lattice, a cellular structure of breathtaking scale and order. Theoreticians like J. Richard Gott III have studied the geometry of the voids, these vast empty bubbles surrounded by the web's filaments. They are not truly empty, but they contain very few galaxies, making them the deserts of the cosmos. The remarkable thing is that this web looks essentially the same in every direction we look, and at every great distance, meaning it has looked this way for billions of years. This incredible uniformity points to a universal set of rules, a fundamental recipe that was followed from the very start. It forces us to look back, beyond the first galaxies, beyond the first stars, to the very initial conditions of the Big Bang itself, to the moment the instructions for this entire cosmic city were first printed. This intricate cosmic web, for all its grandeur, is not a static monument. It is a dynamic system, and at the very heart of its most massive nodes, a powerful regulatory force is at work. Deep within the central galaxies of great clusters, a hidden engine governs the growth of the entire structure. This is the realm of the active galactic nucleus, where a supermassive black hole, feeding on surrounding matter, unleashes energies that can outshine every star in its galaxy combined. But this is not merely a spectacle of raw power. It is a precise, almost surgical mechanism of control. As vast quantities of gas cool and flow inward along the cosmic web's filaments, they are destined to form new stars. Yet, when this process becomes too efficient, when star formation threatens to run wild, the central black hole awakens. It launches colossal jets of charged particles and generates winds that scream outward at nearly the speed of light. These outflows do not destroy the galaxy. Instead, they heat the incoming reservoir of cool gas, preventing it from collapsing further. It is a cosmic thermostat, ensuring the galaxy does not burn through its fuel too quickly. We can see the evidence of this balancing act in stunning X-ray observations from space telescopes like Chandra. In the Perseus galaxy cluster, the images reveal enormous, symmetrical bubbles of ultra-hot gas, each one spanning tens of thousands of light-years. These are not empty voids, but cavities inflated by the relentless pressure of jets from the central black hole. They act like a giant spoon stirring a pot, injecting tremendous energy into the surrounding gas and keeping it from cooling down to form new stars. Astronomer Andy Fabian, who has studied these systems for decades, describes this as a self-regulating feedback cycle. The infalling gas feeds the black hole, which then erupts, shutting off the very supply that feeds it. This creates a remarkable state of cosmic homeostasis, a stable equilibrium where the growth of the black hole and the birth rate of stars are locked in a delicate, opposing dance. This intricate mechanism suggests a level of fine-tuning that is breathtaking. It appears to be a universal rule, a hidden pattern written into the laws of physics itself, ensuring that the most massive structures in the universe do not grow out of control. The very violence of a black hole becomes an essential tool for maintaining cosmic order, a paradox that points to a deeper, more profound design. This leads us to a final, compelling question. If these patterns of structure, growth, and regulation are so universal, what is their ultimate source? Could the entire cosmic story, from the first whisper to the last galaxy, be the consequence of a single, elegant, and fundamental mathematical truth? This hidden alignment of galactic spins is one of the cosmos's most subtle yet profound patterns. Across the vast emptiness, neighboring galaxies are often caught spinning in concert, their axes of rotation mysteriously aligned as if choreographed by an unseen hand. This is not a matter of chance. It is a direct consequence of how the universe imparted a fundamental property to all emerging structures, a property known as angular momentum. To understand this, we must go back to the era of the protogalactic clouds, when the first large structures were just beginning to coalesce from the cosmic web. These infant clouds were not isolated. They were subject to the gravitational tugs of all the matter surrounding them, a complex landscape of overdensities and underdensities. The theory that explains how this environment gave galaxies their spin is called tidal torque theory. Imagine a large, slightly elliptical cloud of gas. The gravitational pull from a neighboring mass will be stronger on the near side of the cloud than on the far side. This difference in force, this tidal pull, does not just stretch the cloud. It applies a twist. It sets the entire cloud spinning, much like you might spin a basketball on your finger by applying an off-center push. In the early universe, every protogalactic cloud was subjected to these tidal torques from the uneven distribution of matter around it. The direction of the spin was locked in by the specific geometry of that initial gravitational landscape. The astonishing part is that this initial flick of spin, this primordial angular momentum, has been largely conserved for over 13 billion years. Once a cloud began to collapse, its spin intensified, just as an ice skater spins faster by pulling their arms in. This conservation law is why we see galaxies rotating at all. But the pattern goes deeper than individual spins. Because neighboring protogalaxies formed from the same large-scale region of the cosmic web, they experienced similar tidal forces from the same overarching matter distribution. Consequently, their spins were imprinted with a coherent direction, creating vast volumes of space where galaxies share a preferred rotational alignment. We can observe this fossilized spin record today by studying the rotation of neutral hydrogen gas in thousands of galaxies. Surveys like ALFA, which maps hydrogen across huge swaths of the sky, provide the data. By carefully measuring the Doppler shift of this radio emission from gas on one side of a galaxy versus the other, astronomers can determine the direction of rotation. When they compile these measurements statistically, the alignments emerge from the noise. The work of cosmologists like Paolo Catalan shows how these spin directions are not random. They are a direct, preserved imprint of the universe's initial conditions, a snapshot of the gravitational tides that existed when the cosmos was only a fraction of its current age. This grand coherence, written in spin, points to an even more pervasive, though invisible, force that may have guided the final assembly of galaxies. It suggests that another architect was at work, weaving threads of magnetism through the primordial chaos. These subtle alignments of galactic spin are not the only invisible threads woven into the cosmic tapestry. Another, even more pervasive force flows through the space between the stars, a silent architect guiding the very gas that gives birth to them. This is the force of cosmic magnetism. Immense magnetic fields generated by powerful dynamo processes permeate the disks of every spiral galaxy. They are not merely passive residents. These fields exert a tangible pressure, influencing how interstellar gas collapses, how stars are born, and even how cosmic rays travel across vast distances. The process that creates and sustains these galaxy-spanning fields is a masterpiece of cosmic engineering. It is known as the Galactic Dynamo. Within the turbulent, rotating disk of a galaxy, the motions of ionized gas act like a colossal electrical generator. This churning, convective motion, combined with the galaxy's overall rotation, amplifies weak, primordial magnetic seeds into the ordered, large-scale fields we detect today. It is a self-sustaining cycle, where kinetic energy from the galaxy's motion is converted into powerful magnetic energy. We can now trace the shape of these invisible architectures. Using sophisticated radio telescopes like the Very Large Array, or VLA, astronomers map the polarization of radio waves emitted by electrons spiraling along the magnetic field lines. This technique allows us to literally see the ghostly outline of a galaxy's magnetic skeleton. When we look at a galaxy like M51, the Whirlpool Galaxy, the results are breathtaking. The magnetic field lines are not a chaotic tangle. They run in an elegant, ordered pattern, closely following the galaxy's grand design spiral arms. It is as if the spiral density wave, which compresses the gas, also combs the magnetic fields into alignment, creating a coherent magnetic highway that stretches for tens of thousands of light years. The work of researchers like Rainer Beck has been pivotal in revealing how these fields are not just tracers of structure, but active participants in the galactic drama. Magnetic pressure provides a subtle but crucial support against the relentless pull of gravity. In a dense cloud of gas, gravity wants to collapse the cloud to form new stars. But the tangled magnetic field within that cloud acts like a cushion of resistance, slowing the collapse and effectively setting the thermostat for star formation. This magnetic influence subtly steers the pace of galactic evolution, preventing a galaxy from burning through its fuel in one frantic burst. It is a regulatory mechanism as sophisticated as the black hole feedback in galaxy clusters, but operating on the smaller, yet equally vital, scale of the interstellar medium. The pervasive and ordered nature of these magnetic fields, built from the inside out by the galaxy's own motion, suggests they are a fundamental, pre-programmed component of the galactic growth blueprint. This intricate interplay between gravity, rotation, and magnetism points to a universe where growth is not a simple contest of forces, but a delicate, choreographed balance. Yet, this internal balance is constantly tested by the galaxy's environment, by the raw material it draws in from the cosmic web itself. The silent, magnetic architecture within a galaxy is constantly tested by the neighborhood it calls home. A galaxy's final form, whether a vibrant spiral or a quiet elliptical, is not just a matter of its internal dynamics. Its fate is profoundly shaped by its location within the vast cosmic web, following a powerful pattern known as the morphology-density relation. In the sparse, quiet suburbs of the universe, the field galaxies, you find a wealth of beautiful, star-forming spirals. Their blue-tinged arms are alive with the glow of young, massive stars, and they possess rich reservoirs of cool gas, the fuel for future generations. But travel into the dense, bustling downtown of a massive galaxy cluster, and the picture changes dramatically. Here, the dominant citizens are smooth, red, elliptical galaxies. They are largely devoid of the gas needed to make new stars, and their stellar populations are old and quiet. This is not a coincidence. It is a direct result of the environment itself, a process astronomers call environmental quenching. One of the most brutal mechanisms at work in these dense clusters is ram pressure stripping. Imagine a spiral galaxy like our own Milky Way, falling for the first time into a giant cluster like Coma. The space between the galaxies in a cluster is not empty. It is filled with a thin but incredibly hot plasma known as the intracluster medium. As the spiral galaxy plunges through this searing gas at millions of miles per hour, it experiences a wind far more powerful than any hurricane. This wind acts like a torrential force, physically blowing the galaxy's own cool gas reservoir right out of its disk. The galaxy is effectively stripped of its star-forming fuel in a single violent episode. We can see the aftermath of this cosmic robbery in stunning detail. In the Virgo cluster, astronomers observe galaxies with long, ghostly tails of gas streaming out behind them, like cometary tails pointing away from the cluster center. These are galaxies caught in the act of having their lifeblood torn away. This relentless environmental influence has not been constant throughout cosmic history. The Butcher-Ohmler effect, a discovery named for astronomers Butcher and Ohmler, reveals that the populations in galaxy clusters were very different in the past. When we look at distant clusters, meaning we see them as they were billions of years ago, we find they contain a much higher fraction of blue, star-forming spirals. Over time, as the universe has aged, those blue galaxies have been transformed. The processes of ram pressure stripping, along with other gravitational harassments, have quenched their star formation, causing them to redden and fade, evolving into the passive red ellipticals that dominate clusters today. This is a clear sign that the cosmic environment is an active and evolving architect, continually reshaping the galaxies within it. The work of astronomers like Alan Dressler helped cement this understanding, showing that a galaxy's morphology is a direct consequence of the local density of its surroundings. The dense core of a cluster is a hostile place for a delicate spiral. The constant gravitational interactions with neighbors, the relentless pressure from the hot intracluster gas, and the sheer tidal forces all work in concert to strip, harass, and ultimately quench a galaxy, transforming its structure and shutting down its star-forming engine. This reveals a profound layer of the cosmic blueprint. The initial conditions of the universe, those tiny ripples that define the cosmic web, did not just dictate where galaxies would form. They also predetermined the types of galaxies that would flourish or falter in each environment. A galaxy's destiny is, in part, written in the location of its birth within the grand cosmic architecture. This intricate connection between a galaxy's fate and its address in the cosmos forces a final, fundamental question. Could all these diverse patterns, from spin to structure to star formation, ultimately be traced back to a single, elegant mathematical origin, a master equation from which the entire universe unfolded? That primordial flick of spin and the cosmic morphology-density relation all trace their lineage back to a single, explosive moment of creation. Every pattern we see in the galaxies, every filament of the cosmic web, was encoded into the universe during its very first fraction of a second. This epoch is known as cosmic inflation, a period of exponentially rapid expansion that stretched the fabric of space itself. In that fleeting instant, the entire observable universe was smaller than a single proton, a realm governed by the bizarre laws of quantum mechanics. Here, at the tiniest of scales, empty space was not truly empty. It was a seething foam of energy, bubbling with fleeting quantum fluctuations. Particles and antiparticles winked in and out of existence, creating a microscopic chaos of density variations. Inflation acted like a cosmic magnifying glass of unimaginable power. It seized these infinitesimal quantum jitters and stretched them across the cosmos, freezing them into the very fabric of spacetime as microscopic ripples in density. These ripples became the seeds for everything, the primordial imprint from which all structure would eventually grow. We can see the direct evidence of this process in the oldest light in the universe, the cosmic microwave background. Space missions like WMAP and Planck have mapped this afterglow with breathtaking precision. Their data reveals a sky painted with tiny temperature variations, hot spots and cold spots that differ by only millionths of a degree. These are not random splotches. They are the fossilized impression of those stretched quantum fluctuations, a baby picture of the universe showing the exact overdensities and underdensities that gravity would later use to build galaxies. Theoreticians like Andre Linde helped develop the framework showing that inflation predicts these initial ripples should have a very specific statistical character, known as a Gaussian random field. This is a sophisticated way of saying the distribution of the fluctuations is perfectly random, yet it follows a precise set of probabilistic rules, much like the outcome of rolling a vast number of dice. When astronomers analyze the Planck data, the pattern of the hot and cold spots matches this Gaussian prediction with stunning accuracy. The statistical properties of these ancient ripples are the exact same properties we later see in the distribution of galaxies across the cosmic web. This is the ultimate connection, the final piece of the architectural blueprint. The specific spectrum of fluctuations imprinted by inflation directly determined the relative numbers of small protogalaxies versus giant galaxy clusters. It set the characteristic distances between the Great Walls and filaments. The entire complex hierarchy of cosmic structure was preordained in that first burst of expansion. This profound realization means that the majestic spiral of a galaxy and the vast emptiness of a cosmic void are both the grown-up children of quantum noise, amplified to a cosmic scale. Yet, this primordial blueprint contains one more specific, testable prediction: a ghostly echo of sound waves from the early universe that would leave a permanent ruler etched into the cosmos, a standard ruler known as baryonic acoustic oscillations. That primordial burst of expansion not only imprinted the seeds of structure, it also gave the universe its very first sound. In the seething plasma of the first few 100,000 years, the cosmos was a roiling, opaque sea. Ordinary matter, the baryons, was locked in a tight embrace with light itself. The photons, gravity, ever persistent, tried to pull the matter into the tiny overdensities left by inflation. But the intense pressure from the trapped photons pushed back, creating a powerful, rhythmic struggle. This conflict set the entire primordial plasma ringing with sound waves, massive compressions and rarefactions that raced outward at over half the speed of light. These are the baryonic acoustic oscillations. Then, around 380,000 years after the Big Bang, the universe cooled just enough for a pivotal event known as recombination. Electrons combined with protons to form the first neutral atoms. In that instant, the photons, suddenly freed from their long entanglement with matter, streamed out across the universe, their pressure support vanishing. The sound waves froze in place, their progress abruptly halted. Each of those frozen waves left a distinct, spherical shell of slightly denser matter, a cosmic ripple with a very specific radius. This radius, the distance the sound wave could travel before the music stopped, became a fundamental standard ruler etched into the cosmos. That preferred scale is about 500 million light-years across. This means that if you could take a census of all the galaxies in a huge volume of space, you would find a subtle but undeniable statistical preference for galaxy pairs to be separated by this specific distance. They are not all spaced this way, but the pattern emerges clearly when you analyze millions of them. It is as if the universe is stamped with a faint, recurring fingerprint. This is the ghostly echo that astronomers now hunt. Massive surveys like the Baryon Oscillation Spectroscopic Survey, or BOSS, and its successor, eBOSS, have meticulously mapped the three-dimensional positions of millions of galaxies. By analyzing this cosmic cartography, they can detect that faint, preferred separation, the BO signal. Because we know the true, physical size of this standard ruler from the physics of the early universe, we can use it as a cosmic tape measure. By observing how the apparent size of this ruler changes across different cosmic epochs, we can trace the expansion history of the universe with phenomenal precision. It acts like a series of mileposts stretching back in time, allowing us to measure how the rate of the universe's expansion has changed over billions of years. The work of cosmologists like Daniel Eisenstein has been instrumental in extracting this signal from the data. What they found was a stunning confirmation of our standard model of cosmology. The BAO measurements independently confirmed the existence of dark energy, the mysterious force accelerating the expansion of the universe. They also provided exquisite constraints on the geometry of the cosmos, showing it to be flat to an incredibly high degree of accuracy. This reliability, this fact that a pattern imprinted in the first fireball remains a trustworthy guide 13 billion years later, speaks to a universe of profound and unwavering order. Yet, this grand, large-scale architecture is only one layer of the cosmic blueprint. Within each individual galaxy, another pattern is being written, one that records its own intricate life story in the language of chemistry. These chemical fingerprints are written in the very stars themselves. A galaxy's core often glows with the distinct, reddish light of ancient, metal-rich suns, while its spiral arms shimmer with the hotter, bluer light of younger, more pristine stars. This is not just a difference in age, but a profound chemical gradient, a record of the galaxy's growth written in the language of elemental abundance. The term metals in astronomy means something far broader than it does on Earth. Here, a metal is any element heavier than hydrogen or helium, These heavier elements, like oxygen, carbon, and iron, are not born in the Big Bang. They are forged exclusively in the nuclear furnaces of stars and scattered into space by the violent deaths of supernova. This means that a star's metallicity, the fraction of its mass made of these heavier elements, is a direct measure of its birth date. The first stars to form in a galaxy were composed of almost pure hydrogen and helium. They lived fast, died young in spectacular supernova explosions, and seeded their surroundings with the very first dusting of heavy metals. The next generation of stars formed from this slightly enriched gas, and so the cycle continued, with each stellar generation increasing the overall metallicity of the galactic raw material. This process did not happen uniformly across a galaxy. It began at the very center. According to the inside-out formation model, the densest, central region of a protogalactic cloud collapses first under its own gravity. This leads to a ferocious burst of star formation in the core. The resulting supernova from this first wave of massive stars then flood the central region with metals, rapidly enriching it. The galaxy's core essentially pollutes itself very early on, creating a concentrated population of old, metal-rich stars. Meanwhile, the outer regions are still slowly accumulating, drawing in fresher, less processed gas from the galactic halo and the cosmic web. This gas has not been through as many cycles of star formation, so it remains metal-poor. As the galaxy grows, new stars continue to form in these outskirts, but they are born from this more pristine fuel. The result is a clear chemical map, a gradient where metallicity steadily decreases as you move from the bustling galactic downtown out to the rural suburbs. We can now read this map with incredible precision. Integral field spectroscopy surveys like the Calar-Alto Legacy Integral Field Area Survey, or CALIFA, have revolutionized our view. Instead of just seeing a galaxy as a single point of light, these instruments take a spectrum for every single pixel in an image. This is like giving astronomers a palette with thousands of tiny paint samples, each one revealing the chemical composition and age of the stars in that specific location. When we apply this technique to a spiral galaxy, the resulting metallicity maps are strikingly clear. They show a smooth, radial decline from the metal-rich center to the metal-poor outer disk, a beautiful and direct confirmation of the inside-out growth model. Astrophysicist Lisa Cooley's work has been pivotal in interpreting these chemical clocks. She explains how these gradients are not static. They are a dynamic record, sensitive to a galaxy's entire history. A major merger with another galaxy can churn up the disk, mixing the metal-rich and metal-poor gas and flattening the gradient. A steady stream of fresh, low metallicity gas flowing in from the cosmic web can dilute the outer regions, making the gradient even steeper. The specific shape of the metallicity profile, therefore, tells a story. It reveals whether a galaxy grew peacefully through steady accretion or was violently shaken by past encounters. This chemical record extends even beyond the visible edge of the main galaxy. When we look at the small satellite galaxies orbiting a giant like our Milky Way, we find that their stars are typically far more metal-poor than those in the main galactic disk. This makes perfect sense within our story of inside-out growth. These dwarf galaxies represent the first, small fragments to collapse in the early universe. They began their own, independent star formation with very little initial gas, quickly used up their fuel, and were then cut off from fresh inflows by the gravitational dominance of the larger galaxy. Their star formation was stunted early, freezing their metallicity at a low, primitive state. They are cosmic fossils, preserving the chemical conditions of the early universe, while their giant host continued to evolve and enrich itself. This intricate chemical archaeology reveals that a galaxy is not a monolithic object, but a stratified history book. Its center holds the oldest, most processed chapters, while its outer pages tell a younger, more primordial tale. Every star is a time capsule, and their collective metallicity paints a detailed portrait of the galaxy's assembly. Yet, this portrait is constantly being updated, as new material continues to rain down from the vast reservoir of the circumgalactic medium, the final frontier in our search for the architects of galactic growth. This organized alignment of satellite galaxies presents a profound puzzle. Our own Milky Way is not an isolated island, but the center of a small gravitational empire, orbited by dozens of smaller dwarf galaxies. According to our most successful cosmological models, these satellites should be scattered around us in a roughly spherical swarm, like bees buzzing randomly around a hive. Yet when astronomers like Pavel Krupa began mapping their precise positions, they found something entirely different. Many of the Milky Way's satellites are not randomly distributed at all. Instead, they are arranged in an astonishingly thin, vast, rotating plane, a structure now known as the vast polar structure. This is not a unique quirk of our galactic neighborhood. Our great neighbor, the Andromeda Galaxy, also displays a similar, thin plane of co-rotating satellites. This is a major conundrum. In the standard model of cosmology, galaxies form within enormous, lumpy halos of dark matter. These halos should act like a kind of invisible, sticky gel, trapping satellite galaxies and causing them to fall into the main galaxy from all directions, resulting in a chaotic, spherical distribution. The existence of these thin, rotating planes of satellites is like finding all the bees dutifully circling the hive in a single, flat disk, a configuration that the dark matter model struggles to produce in its simulations. How could such delicate, coherent structures persist? One compelling idea is that these satellite planes are not primordial objects at all, but are instead the result of a more recent, violent event. They could be tidal dwarf galaxies, born from the colossal collision of two larger galaxies in the distant past. When two massive galaxies graze each other, their mutual gravity can pull out immense streams of gas and stars. Within these tidal tails, the density can become high enough for new, small galaxies to condense. Because they all form from the same debris disk, these newborn tidal dwarfs would naturally share the same orbital plane, neatly explaining the observed alignment. This would mean that some of the satellites we see are not ancient relics, but second-generation galaxies with a very different origin story. Another, more radical possibility is that our understanding of dark matter itself requires revision. Perhaps dark matter is not completely cold and collisionless. Maybe it possesses some form of weak interaction, or is influenced by long-range forces that allow it to form such thin, coherent disks on galactic scales. The persistence of these aligned systems points to a formation process that is far more coherent and structured than our standard pictures allow. It suggests that the influence of the larger cosmic environment, the filaments of the cosmic web, might be guiding these satellites into their aligned orbits, like rivers channeling logs into a single, floating raft. This satellite conundrum forces us to look beyond gravity alone. To solve it, we must consider another, more energetic architect, one that flows through the galaxy at nearly the speed of light, the mysterious and powerful influence of cosmic rays. These cosmic ray particles, accelerated to nearly the speed of light, are a fundamental force in the galactic ecosystem. They do not simply streak through empty space. They interact profoundly with the galaxy's magnetic architecture, creating a form of pressure that can rival both thermal heat and magnetic fields. When a massive star ends its life in a supernova explosion, the expanding shock wave acts like a natural particle accelerator. It can fling atomic nuclei, mostly protons, across the galaxy with unimaginable energy. These are cosmic rays. They do not travel in straight lines. Instead, they spiral along the invisible pathways of the galactic magnetic field, their paths tangled and twisted by this force. This constant, chaotic motion has a tangible effect. It creates a diffuse pressure that permeates the entire interstellar medium, much like the air pressure in a balloon. This cosmic ray pressure becomes a crucial component in the balance of forces within a gas cloud. Gravity wants to pull the cloud inward to form new stars. The thermal pressure of the hot gas and the magnetic pressure both push back. Now we must add the relentless push from these high-energy particles. In some environments, especially in galaxies with vigorous star formation, the cosmic ray pressure can become the dominant force resisting gravity. It can help support giant molecular clouds against collapse, effectively putting a brake on the rate of star formation. We can now witness this energetic interplay directly. Space telescopes like the Fermi Large Area Telescope, or Fermi LAT, do not see the cosmic rays themselves. Instead, they detect the telltale gamma rays produced when these high-speed particles collide with the slower-moving nuclei of interstellar gas. These gamma-ray observations allow us to map the distribution of cosmic rays across the Milky Way. What they reveal is a galaxy suffused with this invisible energy, with particularly intense glow coming from regions rich in supernova remnants, confirming their role as cosmic ray factories. Ground-based observatories like the High-Altitude Water Cherenkov Observatory, or HAWK, complement this view by detecting even higher-energy gamma rays, painting a more complete picture of the cosmic ray population. The influence of these particles extends far beyond the galactic disk. This is where their role becomes truly transformative. The pressure exerted by cosmic rays is exceptionally efficient at driving material upward and outward. Unlike thermal gas, which can cool and lose its pressure, cosmic rays lose their energy very slowly. This allows them to act as a persistent piston. They can push against the gravitational pull of the galaxy, lifting vast reservoirs of gas clear out of the disk and launching them into the halo. These are galactic winds, colossal outflows that carry mass and energy from the star-forming regions into the circumgalactic medium. Astrophysicist Ellen Zweibel has extensively studied this process, describing how cosmic rays, in concert with magnetic fields, can launch these winds with remarkable efficiency. The cosmic rays essentially help the galaxy breathe out, expelling material that might otherwise have formed new stars. This outflow does more than just deplete the fuel supply. It enriches the space around the galaxy. The gas driven out by these winds is often metal-rich, having been forged in the hearts of stars and supernova. This process transports these heavy elements far into the galactic halo, seeding the circumgalactic medium with the chemical building blocks for future generations of stars and planets. It is a form of large-scale recycling, a feedback loop where the death of stars, through supernova and their cosmic rays, directly regulates the birth of new ones. This cosmic ray feedback represents a sophisticated layer of regulation, operating alongside the more violent feedback from supermassive black holes. It is a gentler, more continuous process, a steady wind rather than a violent eruption, yet it is no less crucial for maintaining the long-term balance of a galaxy. This intricate dance of forces, from the quantum to the cosmic, hints at a universe where every component, even the most energetic particles, plays a prescribed role in a grand, self-regulating design. This relentless cosmic wind, driven by the ghosts of dead stars, is but one force shaping a galaxy's destiny. A far more dominant power now governs the cosmos, one that writes the final chapter for every structure we see. Dark energy, the mysterious agent driving the universe's accelerated expansion, holds the ultimate blueprint for all galactic futures. Its influence is not a distant possibility, but a present reality that is already reshaping the cosmic landscape. Think of the universe's energy budget as a vast pie. For billions of years, the gravitational pull of matter, both dark and ordinary, was the dominant slice. This gravity worked to pull structures together, building the cosmic web. But around 5 billion years ago, a cosmic tipping point was reached. Dark energy, which behaves like a kind of anti-gravity inherent to space itself, became the dominant component of the universe. As the universe expanded and became more diffuse, matter's density dropped, while the density of dark energy remained constant, or possibly even increased. This is why dark energy now makes up about 70% of all the energy in the cosmos, with dark matter and ordinary matter making up the rest. The consequence of this dark energy dominance is a profound and chilling change in the rules of cosmic construction. The accelerating expansion it causes is stretching the very fabric of the cosmic web. The great filaments that once channeled gas into the waiting arms of galaxies are being pulled taut, like strands of taffy. The flow of fresh, pristine hydrogen from the cosmic highways is slowing to a trickle. In the future, this flow will stop entirely. The formation of new galaxies, which has continued for over 13 billion years, will cease. Our universe's era of galaxy building is coming to an end. Cosmologists model this future using our most successful cosmological framework, the Lambda Cold Dark Matter model. The predictions are starkly beautiful. Galaxy clusters, the great metropolises of the cosmos, will not merge into ever larger structures. Instead, they will become isolated islands. The space between these island universes will expand at an ever-increasing rate, eventually moving faster than the speed of light. The light from one cluster will never again reach another. Each cluster, with its thousands of galaxies, will become a lonely cosmic city, its borders forever fixed, floating in an infinite and ever-darkening void. This is not just theoretical. The observational evidence for this accelerating fate was first solidified by teams studying distant supernova. Astronomers like Dr. Wendy Friedman played a crucial role in calibrating the cosmic distance ladder, providing the precise measurements needed. By observing Type 1, a supernova, which have a known intrinsic brightness, in galaxies billions of light-years away, two independent teams made the same shocking discovery in the late 1990s. These stellar explosions were fainter than expected, meaning they were farther away than they should have been in a universe slowing down from gravity. The only explanation was that the expansion of the universe is accelerating, propelled by this mysterious dark energy. This discovery connected the grandest scale of cosmic fate directly back to the intricate patterns we see in individual galaxies. The same force that will one day isolate all galactic structures is the same force that influenced how they spun and assembled in the first place. It is the ultimate architect, setting the initial conditions, overseeing the growth, and now writing the final, quiet epilogue. This cosmic trajectory from a hot, dense beginning to a cold, isolated end seems to be the universe's inevitable story. Yet, this very story, written in the fading light of supernova, depends entirely on the precise values of fundamental numbers, numbers that appear fine-tuned to an astonishing degree, pointing toward a final, deeper mystery. This radical idea suggests that the universe we perceive might be a magnificent illusion. The holographic principle turns our intuition about reality inside out, proposing that all the information contained within any three-dimensional volume of space, including every galaxy and star, is actually encoded on its two-dimensional boundary. Think of the universe not as a solid object, but as a cosmic hologram. The three-dimensional world we experience could be a projection from a vast, two-dimensional surface at the edge of everything, a surface that holds all the information needed to describe our reality, much like a hologram on your credit card projects a three-dimensional image from a flat, two-dimensional film. This is not just a metaphor. It is a serious theoretical framework developed by physicists like Leonard Susskind and Gerard T. Hooft, building on our understanding of black holes. Their work revealed a profound puzzle. The amount of information a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was the first clue that the fundamental description of a space might reside on its surface, not within its bulk. The most concrete realization of this principle came from physicist Juan Maldacena. He discovered a precise mathematical duality, a kind of dictionary, between a gravitational theory operating in a hypothetical five-dimensional space and a quantum field theory living on its four-dimensional boundary. This AD-S/CFT correspondence, as it is known, provides a full-fledged example of holography in action. It shows that a complex system involving gravity in a higher dimensional world can be perfectly described by a quantum theory without gravity on its lower dimensional boundary. If this principle applies to our own universe, the implications for galactic architecture are staggering. The intricate three-dimensional cosmic web, with its vast filaments and brilliant galaxies, would not be the fundamental reality. It would be an emergent property, a grand projection of information encoded on a distant, two-dimensional surface. The hidden patterns controlling galactic growth, from the density fluctuations of the early universe to the feedback loops of black holes, would all be manifestations of a simpler, more fundamental quantum system operating on this cosmic boundary. This framework would revolutionize our search for the architects. We would no longer look for forces and laws operating solely within the space we see. Instead, we would search for the fundamental rules of information processing on this lower dimensional surface. The birth of a galaxy, the spin of its stars, and the flow of its magnetic fields could all be computations in this vast cosmic code. This speculative vision challenges the very core of cosmology, urging us to consider that the ultimate architects of infinity are not forces of nature, but the fundamental laws of information itself. Deep within the cold, dark nurseries of molecular clouds, a chaotic force sculpts the future of stars. This is not a gentle process, but a supersonic storm of interstellar turbulence. Driven by the shockwaves of supernova explosions, the relentless pressure of stellar winds, and the sheer spin of the galaxy itself, this turbulence churns the gas into a fractal-like tapestry of filaments and knots. It is this very chaos that imposes a strange and beautiful order on star formation. The turbulent motions create a vast spectrum of densities within a cloud. Most of the cloud remains diffuse, but the flows collide, forming dense pockets where gravity can finally take hold. Only the very densest of these knots, shielded from the dissipating pressure of the surrounding turmoil, can collapse to ignite new suns. This relationship between the speed of turbulent motions and the size of a cloud region follows a precise mathematical pattern, known as the Larson scaling laws. It is a power law relation that reveals a universe where chaos itself is governed by a hidden rule. We can now witness this violent genesis through groundbreaking supercomputer simulations like the Starforge project. These are not simple animations. They are virtual universes that model the supersonic flows of gas with incredible fidelity, tracking the birth of individual stars from the turbulent cascade. The simulations show how random motions, following the Larson relations, generate a hierarchy of structures. Small, transient clumps form and are torn apart, while larger, more stable cores coalesce, their fate hanging in the balance between the inward pull of gravity and the outward push of turbulent pressure. The result of this cosmic dance is the initial mass function, the distribution of stars by size. Why are there so many small red dwarfs for every massive blue giant? The answer is written in the statistics of turbulence. It dictates the probability of forming a dense core of a given mass, thereby setting the blueprint for the stellar population of an entire galaxy. According to astrophysicists like Dr. Christoph Federath, this creates a global equilibrium. Turbulence is a double-edged sword. On one hand, it creates the high-density seeds necessary for star birth. On the other, it provides a form of support that can prevent entire clouds from collapsing in a single, catastrophic burst. The powerful shockwaves from newly formed massive stars, which quickly explode as supernova, inject more energy back into the cloud, stirring the turbulence and shutting down further collapse nearby. This feedback loop ensures that star formation is a slow, regulated process rather than a runaway chain reaction. A galaxy does not simply convert all its gas into stars at once. It manages its resources over billions of years. This intricate self-regulation is so fundamental that its specific efficiency appears to be fine-tuned. The balance point between promoting and suppressing star formation seems to depend on the precise values of fundamental constants in nature, like the strength of gravity or the mass of a proton. It is as if the universe's recipe for building stars was calibrated from the very beginning to ensure a long and structured evolution, leaving one to wonder if this turbulent regulation is not just a physical process, but a deeply embedded cosmic command. The precise calibration of these physical laws is so exact it feels almost intentional. The strength of gravity, the force binding atoms, the mass of an electron, these are not arbitrary numbers. They are the universe's fundamental settings, and they appear to be fine-tuned to an astonishing degree for the emergence of complexity. Alter any one of these constants even slightly, and the entire cosmic architecture we have explored would simply collapse. Consider the gravitational constant. If gravity were just a tiny bit stronger, the universe would have collapsed back on itself in a catastrophic big crunch long before galaxies could ever form. If it were even a fraction weaker, matter would have flown apart so rapidly that not even the faintest protogalactic cloud could have condensed from the primordial haze. The fine structure constant, which governs the strength of electromagnetism, is another example of breathtaking precision. If this number were larger, protons would repel each other so fiercely that atomic nuclei could never fuse together. Stars would never ignite. If it were smaller, atoms would be unstable, and the complex chemistry that forms planets and life would be impossible. The cosmos would be a dark, sterile sea of hydrogen. Physicists like John Barrow have meticulously calculated the narrow window within which these constants must lie to permit a universe of long-lived stars and structured galaxies. His work reveals that the allowed range for variation is infinitesimally small. We exist in a universe that seems perfectly tailored for our own existence, a concept known as the anthropic principle. This observation leads to a profound and controversial question. Why is the universe so hospitable? One compelling answer is the multiverse theory. This idea suggests our universe is just one bubble in a vast, perhaps infinite, cosmic foam. In this grand ensemble, each universe is born with its own random set of physical constants. In the overwhelming majority of these universes, the numbers are wrong. Gravity is too strong, electromagnetism is too weak, and the cosmos remains dark, empty, or fleeting. But by pure chance, in a tiny fraction of them, the numbers line up perfectly. We, of course, find ourselves in one of those rare, Goldilocks universes where the conditions are just right for galaxies to shine and for life to ponder their origins. This multiverse concept offers a naturalistic explanation for the apparent fine-tuning, framing our cosmic home not as a unique creation, but as a statistical inevitability in an immeasurably vast reality. Yet, for some, this remarkable precision, this sense of a universe built on a razor's edge, hints at a deeper level of architectural design, a necessity woven into the fabric of reality itself. Whether by chance in a multiverse or by some deeper principle we have yet to uncover, this fine-tuning is the ultimate foundation for every pattern we see, setting the stage for the final, quiet destiny of all galactic structures. This grand cosmic story, for all its intricate patterns, is moving toward a final, silent conclusion. The vibrant era of galactic growth we witness today is but a brilliant, fleeting flash in an unimaginably long cosmic timeline. Over trillions upon trillions of years, The universe will continue along the path set by dark energy, evolving toward a state known as the heat death. In this distant future, the very structures we call home will undergo a profound and irreversible transformation. The first change is the end of star formation. One by one, galaxies will exhaust their reservoirs of cold molecular gas. With no fresh fuel to create new suns, the last generation of stars will ignite. These will be small, dim red dwarfs, stars so frugal with their hydrogen fuel that they can shine for trillions of years. But even they are not eternal. Eventually, the last red dwarf will flicker out, its nuclear fires extinguished forever. The galaxy will then be populated by the corpses of stars, white dwarfs that slowly cool into black dwarfs, and neutron stars that gradually fade. The universe will redden, then dim, as the brilliant blue light of young stars vanishes from the cosmos, leaving only the faint, deep red glow of aging suns. The dynamic dance of galactic mergers will also cease. As dark energy relentlessly stretches the cosmic web, the great filaments will be torn apart. Galaxy clusters, once bustling cities, will become isolated islands, their gravitational ties to each other severed. No new material will flow in, and no galactic collisions will stir the stellar populations. The universe will grow not only dark, but also still. This is the vision detailed by cosmologists like Dr. Fred Adams in his work on the far future of the universe. But the story does not end with cold, dark stars. On timescales so vast they defy comprehension, the very building blocks of matter may themselves become unstable. A theoretical process known as proton decay suggests that the protons which constitute all atomic nuclei are not truly permanent. If this theory is correct, over a timescale of 10 to the 34 years or more, all baryonic matter, everything made of atoms, from the coldest black dwarf to the last dust grain, will simply dissipate, dissolving into radiation and subatomic particles. Even the most formidable structures, the supermassive black holes at the centers of dead galaxies, are not immortal. Through a quantum process called Hawking radiation, they will slowly evaporate, releasing their immense mass back into the universe as a faint whisper of particles over an almost infinite span of time. The end result is a universe that is profoundly dark, incredibly dilute, and utterly silent. A near-perfect vacuum where the temperature uniformly approaches absolute zero. This eschatological view presents a stark contrast to the vibrant, structured cosmos we see today. It frames our current epoch, this age of brilliant galaxies and shining stars, as a magnificent but transient phase. The majestic spiral arms and glowing stellar nurseries are a direct testament to the specific initial conditions imprinted during the Big Bang, a fleeting window of cosmic activity and light. This inevitable fade to black prompts a powerful reflection. If all galactic structures are destined for this cold, dark end, then the only way to understand their full story is to look backward, to become cosmic archaeologists sifting through the fossils of the universe's vibrant past. The stars themselves are history books, their light a fossil record of the galaxy's violent past. We can now read this galactic archive, reconstructing our Milky Way's assembly through a field known as Galactic Archaeology. This is not about digging in the dirt, but about decoding the subtle messages written in starlight. The key to this cosmic detective work lies in mapping the positions, motions, and chemical compositions of millions upon millions of individual stars. This is precisely what the European Space Agency's Gaia mission has accomplished. Gaia has provided us with a staggeringly precise dynamic map of our celestial neighborhood, charting the paths and properties of over 1 billion stars. By analyzing this vast dataset, astronomers like Dr. Amina Helmi can identify groups of stars that move in concert, like schools of fish in a vast ocean, their shared motion betraying a common origin from a single, devoured galaxy. One of the most dramatic discoveries from this work is the ghost of a galaxy named Gaia Enceladus. Its stars are now thoroughly mixed with our own, but their chemical fingerprints and unique orbital paths give them away. These stellar fossils are old and metal-poor, telling us that Gaia Enceladus was a smaller, primitive galaxy that collided with the infant Milky Way around 10 billion years ago. This colossal merger fundamentally reshaped our galaxy, contributing a vast population of stars to what we now call the stellar halo, a sparse, spherical cloud of ancient suns that surrounds the main galactic disk. The structure of the Milky Way itself is a layered timeline of these events. The halo contains the oldest stars, the first inhabitants and the captured remains of early mergers like Gaia Enceladus. Below it lies the thick disk, a population of intermediate-age stars likely puffed up by the gravitational turmoil of that ancient collision. And finally, there is the thin disk, a delicate, rotating plane where our own sun resides, representing the most recent and orderly phase of the galaxy's growth, built from quieter, steady accretion of gas. This clear stratification directly confirms the hierarchical model of galaxy formation. Our galaxy was not born in its current majestic form. It was assembled piece by piece over billions of years, with its growth spurts and violent mergers literally frozen in the orbits and chemistries of its stars. The work of galactic archaeologists connects directly to the chemical gradients we observed earlier. The stars from the Gaia Enceladus merger are metal-poor, a testament to their early formation in a small, stunted system, while the stars of the thin disk are more enriched, having formed from gas that was cycled through many generations of stars within the growing Milky Way. This historical perspective allows us to test the grand patterns of cosmic growth on our own galactic doorstep, proving that the blueprint for construction applies even here in our own home. It reveals that our solar system is a latecomer, orbiting within a stable disk that was only made possible by the violent construction projects of the deep past. This predictable relationship between gas and starlight is one of the cosmos's most reliable rules. Across the vast diversity of galaxies, from serene spirals to colliding giants, a tight correlation emerges. Wherever you find a high density of interstellar gas, you will find a correspondingly high rate of new star formation. This is the Kennecutt-Schmidt Law, a fundamental equation that quantifies the very heartbeat of a galaxy. It reveals that the conversion of raw gas into brilliant stars is not a chaotic free-for-all. It is a regulated, almost mechanical process that operates under a universal set of instructions. The physics behind this elegant rule is a delicate balancing act. On one side, gravity works tirelessly to pull vast clouds of gas together, encouraging them to collapse under their own weight. This tendency is described by the tumor stability criterion, which essentially sets a minimum density threshold a gas cloud must reach before it can fragment and form stars. It acts like a cosmic gatekeeper, ensuring that only the densest, most unstable regions of a galaxy's disk can proceed with stellar construction. Yet, if gravity acted alone, galaxies would burn through their entire fuel reserve in a single, frantic burst of star formation. This is where feedback enters the stage. The very first massive stars to ignite in a newborn cluster unleash a torrent of energy. Their intense radiation and powerful stellar winds, followed by eventual supernova explosions, blast through the surrounding cloud. This violent output heats and disperses the remaining gas, shutting down further collapse in that immediate area. It is a self-limiting cycle, where star birth sows the seeds of its own temporary destruction. The work of astronomer Robert Kennecutt was pivotal in mapping this relationship across dozens of galaxies, transforming it from a curious trend into a cornerstone of modern astrophysics. The true power of this law is its universality. When we peer back in time to high redshift galaxies, we see the same rule in action, even in the more chaotic, gas-rich environments of the early universe. These primordial galaxies were often veritable factories of star formation, and the Kennecutt-Schmidt Law helps us understand why. Their gas disks were denser and more massive, naturally leading to the ferocious star-forming rates we observe. This empirical rule is so robust that it has become a critical ingredient in the most sophisticated cosmological simulations. When computer models like Illustris TNG seek to build virtual universes, they must program in a version of the Kennecutt-Schmidt Law to ensure their digital galaxies form stars at a realistic and observed rate. It is the essential algorithm that bridges the gap between the simple accumulation of gas and the complex emergence of stellar populations. This predictable pattern underscores a profound truth about cosmic evolution. The growth of galaxies, for all its apparent grandeur, follows a set of quantifiable, physical principles that are consistent across both space and time. This very predictability now allows us to ask an even deeper question about the origins of these galactic systems, a question that takes us back to the very edge of the observable universe. These ancient galactic blueprints reveal a universe in constant flux, where even the dimensions of galaxies are not fixed. We now observe that galaxies of a given stellar mass were significantly more compact in the distant past, growing in physical size over billions of years. This gradual enlargement is not a simple puffing up, but a carefully regulated process of architectural expansion, driven by a steady rain of fresh material from the cosmos. The evidence for this growth is etched into the deep fields of space. When astronomers point the Hubble Space Telescope to a seemingly empty patch of sky for the ultra-deep field exposure, they are looking back in time, capturing the faint light of galaxies when the universe was just a fraction of its current age. What they see are not the grand, sprawling spirals of today, but tiny, dense cores. These primordial galaxies are compact powerhouses, blazing with star formation but confined to a region much smaller than our Milky Way's current disk. The question then becomes, how did these dense seeds unfurl into the vast structures we see today? The answer lies in a delicate, continuous feeding process. While major mergers cause violent and dramatic transformations, the primary mode of growth for most galaxies is far more sedate. It involves a gentle, persistent accretion of cold gas, streaming in from the vast reservoirs of the intergalactic medium. Think of it not as a catastrophic collision, but as a slow, nourishing rain that falls onto the galactic disk from the circumgalactic environment. This is where the work of theorists like Avishai Deckel becomes pivotal. His research describes how these cold flows of pristine hydrogen gas manage to penetrate the hot halo of dark matter surrounding a galaxy. Instead of being heated to millions of degrees and becoming inert, these rivers of cold gas flow along the filaments of the cosmic web, slipping through to deliver their fuel directly to the outer regions of the galactic disk. This process is beautifully self-regulating. The incoming gas is cold and dense, making it the perfect raw material for building new stars. But because it arrives gradually and in the galaxy's outskirts, it does not trigger the kind of frenzied starburst that a major merger would. Instead, it leads to a very specific kind of growth, known as inside-out formation. The galaxy's central ancient core was built first, in that initial, rapid collapse. Now, new stars are born primarily in the outer disk, slowly extending the galaxy's visible boundary and increasing its overall radius. You can picture a city that built its downtown first, and is now steadily adding new suburbs along its perimeter. This continuous accretion of cold gas provides the literal fuel for this suburban expansion. Each new generation of stars formed in the outer disk adds to the galaxy's total stellar mass while simultaneously stretching its physical size. This explains the observed correlation between a galaxy's mass and its diameter, and why that diameter has increased over cosmic time. It is a testament to a universe where growth is often a quiet, persistent process, a steady-handed architect adding new wings to a cosmic mansion according to a pre-drawn plan. This gentle rain of gas, so crucial for galactic expansion, is itself governed by the larger cosmic environment, raising the question of how this intergalactic fuel supply is itself maintained and distributed across the eons. This vast reservoir of galactic fuel exists in the space between all things, a diffuse ocean of plasma known as the Intergalactic Medium. It is not a perfect vacuum, but rather a tenuous sea of ionized gas that holds the majority of the universe's ordinary or baryonic matter. Every galaxy, from the smallest dwarf to the largest spiral, is born from this raw material and continues to draw upon it for growth. The structure of this cosmic reservoir is dictated by the grand architecture of the cosmic web. The dark matter filaments that define the web's skeleton are also traced by rivers of this warm, hot intergalactic gas. Where these filaments intersect at the great nodes of the cosmic web, the gas becomes denser and hotter, often falling into galaxy clusters and feeding the supermassive black holes at their hearts. But along the quieter filaments, the gas can cool, condense, and steadily flow toward waiting galaxies, providing the continuous nourishment needed for sustained star formation. We can actually map this invisible, all-pervading ocean. The key lies in the light of the most brilliant beacons in the universe, quasars. As the intense light from a distant quasar travels across billions of light years to reach our telescopes, it passes through these filaments of intergalactic gas. Specific elements within that gas, like hydrogen, helium, and carbon, absorb very particular wavelengths of that light. This creates a unique fingerprint, a series of dark absorption lines in the quasar's otherwise smooth spectrum. By analyzing these lines, astronomers can determine not only the composition of the gas, but also its temperature, density, and even its motion. It is like taking an X-ray of the cosmos, revealing the intricate bones of the cosmic web that would otherwise remain completely hidden from our view. The pioneering work of astronomers like Professor John Stock has used this technique to chart the evolution of the intergalactic medium over cosmic time. His studies show that this vast reservoir has undergone profound changes. In the early universe, it was a cooler, more neutral fog. But as the first galaxies and quasars ignited, their intense ultraviolet radiation flooded the cosmos, re-ionizing the gas and heating it over billions of years. This means the properties of the gas that falls onto a galaxy today are different from the pristine fuel that built the first stars. The intergalactic medium is not a static resource. It is an evolving component of the cosmic ecosystem, its history written in the absorption lines of quasar light. The stunning realization is that this vast reservoir is imprinted with the same patterns that govern the galaxies themselves. The same gravitational blueprint that arranged the cosmic web also organized the distribution of this intergalactic gas. The statistical fluctuations we see in the galaxy distribution are perfectly mirrored in the distribution of this diffuse plasma. This confirms a profound unity, a single set of architectural rules that operates from the largest scales of the web down to the gaseous fuel for individual stars. Yet this delicate cycle of accretion is a two-way street. For galaxies to maintain their equilibrium, they must not only take in but also give back. This leads to the final, powerful force in the galactic growth equation, the great galactic winds that blow material out of the galaxy and back into the intergalactic medium from which it came. These great galactic winds are the final, vital step in the cosmic recycling process. They do not merely blow gas out into emptiness. They actively seed the vast intergalactic medium with the heavy elements forged in stellar hearts, polluting the primordial reservoir and forever altering the chemical future of the cosmos. This colossal outflow is driven by two immense engines. The first is the collective fury of supernova. When a generation of massive stars dies in quick succession, their explosions create a super bubble of hot, high-pressure gas that punches through the galactic disk, venting its contents into the halo. The second engine is the active galactic nucleus, the supermassive black hole at a galaxy's center. When it feeds, it can launch jets and radiation-driven winds of unbelievable power, capable of heating and expelling gas from an entire galaxy. We can witness this dramatic process in our own cosmic backyard. The galaxy M82, known as the Cigar Galaxy, is a nearby starburst galaxy where star formation is occurring at a ferocious rate. In stunning composite images, we see the main body of the galaxy edge on, a bright bar of light. But shooting out from its center, perpendicular to the disk, are vast plumes of hydrogen gas, glowing with a deep red hue. These are the galactic winds, visible proof that material is being violently ejected. When we look with X-ray telescopes like Chandra, we see these same outflows glowing with incredibly hot, metal-rich gas, a direct testament to the supernova enrichment happening within. The efficiency of this process is measured by what astronomers call the mass loading factor. This is simply the ratio of the mass flowing out in the wind to the mass being converted into new stars. It is a crucial number that tells us how effective a galaxy is at regulating its own growth. The work of researchers like Dr. Crystal Martin has been key in showing that this factor is not constant. It depends profoundly on the galaxy's mass and its star formation rate. In small, low-mass galaxies, gravity's grip is weak. A relatively small amount of energy from supernova can launch a powerful wind, leading to a high mass loading factor. These dwarf galaxies can effectively blow out a large fraction of their gas, quenching their own star formation and enriching the surrounding space. In contrast, a massive galaxy has a much stronger gravitational pull. It takes a far more energetic event, like an outburst from its central black hole, to launch a significant wind. Here, the mass loading factor is lower, and the outflows are more selective, but they can travel much farther, seeding the entire circumgalactic medium with metals. This intricate relationship means that the growth of galaxies is intrinsically linked to their ability to expel their own building materials. It is a self-regulating cycle where the very act of creating stars produces the energy that can eventually shut down that creation. This recycling ensures that no galaxy is an island. The heavy elements born in one stellar nursery can be carried across thousands of light years, eventually becoming part of a new cloud of gas that will one day collapse to form a new star, perhaps one with rocky planets and the potential for life. The iron in your blood and the calcium in your bones were once part of such a cosmic wind, blown from a galaxy long before our own sun was born. This grand-scale pollution reveals a universe deeply interconnected, where the life cycle of one galaxy directly influences the chemical destiny of all others. Even the largest cities in the cosmos follow a strict building code. Galaxy clusters, the immense metropolises containing thousands of galaxies, are not chaotic sprawls. They are organized structures that, despite their different histories of violent assembly, all share a set of remarkable uniformities. Their vast atmospheres of superheated gas, which glow brightly in X-rays, all exhibit a similar temperature profile. This state, known as an isothermal profile, means the searing plasma maintains a surprisingly consistent temperature from the bustling core all the way out to the sparse suburban edges. How can something so vast and turbulent achieve such thermal equilibrium? The answer lies in the very violence of their creation. These clusters were built through a process called hierarchical clustering, a relentless sequence of mergers where smaller groups of galaxies smash together to form larger ones. With each colossal collision, the resulting chaos acts like a giant mixer. The process of violent relaxation, a gravitational phenomenon where the orbits of galaxies and dark matter are completely scrambled, effectively erases the memory of their initial conditions. It does not matter if one protocluster was slightly denser or hotter than another. After billions of years of this gravitational pounding and mixing, they all settle into the same basic, relaxed configuration. This is why the temperature of the intracluster gas smooths out, creating that consistent isothermal profile we observe. We can see this grand uniformity directly thanks to space observatories like Chandra. By mapping the X-ray glow of this hot gas, Chandra does more than just measure temperature. It reveals the hidden hand of dark matter. The distribution and temperature of the gas are entirely dictated by the shape of the gravitational well it sits in, a well carved almost entirely by invisible dark matter. We can independently map this dark matter scaffold through the subtle warping of background galaxies, an effect called gravitational lensing. When we compare the two maps, the X-ray gas and the dark matter halo, they align perfectly. This confirms that the entire system, both seen and unseen, has settled into a state of virial equilibrium, a stable balance between the kinetic energy of its components and the gravitational pull holding it all together. This leads to another profound uniformity, a tight relationship between a cluster's total mass and its X-ray luminosity. Heavier clusters, with their deeper gravitational wells, compress the intracluster gas to higher densities and temperatures, causing it to shine more brilliantly in X-rays. This relationship is so predictable that cosmologists like Dr. August Everard have shown galaxy clusters can be used as standard candles. By simply measuring a cluster's X-ray brightness, we can infer its total mass with remarkable accuracy. This turns these colossal structures into cosmic weighing scales, allowing us to measure the vast distances and the distribution of matter across the universe. The fact that this works for clusters billions of light-years away tells us this uniformity is a fundamental feature of cosmic architecture. It is a pattern stamped into the largest structures by the relentless, predictable laws of gravity and thermodynamics. This consistency is a powerful prediction of our standard model of cosmology, a model we can now test in a completely new way by listening to the echoes of the most violent events in the universe, the collisions of black holes that send ripples through spacetime itself. The violent mergers of galaxies culminate in a final, invisible collision deep within their cores. When two supermassive black holes, each weighing millions of suns, spiral toward each other, they do not emit light. Instead, they shake the very fabric of spacetime, sending out ripples known as gravitational waves. These are not the high-frequency chirps detected from stellar mass black holes. The waves from these cosmic giants are immense, low-frequency hums that stretch and compress space itself over periods of years. For now, this cosmic symphony is silent to our ears, a deep bass note rumbling below the range of our current instruments. But a new era of listening is about to begin. The Laser Interferometer Space Antenna, or LISA, is a future observatory designed to float in space, its 3 spacecraft forming a triangle millions of kilometers across. This colossal instrument will be tuned to the low-frequency gravitational wave band, finally allowing us to hear the universe in a way we never have before. What will this new sense reveal? It will open a direct window into the dark hearts of galactic nuclei. Every major galaxy merger we have discussed ultimately leads to this event. As the black holes finally merge, the properties of the gravitational waves they emit, their frequency, amplitude, and evolution, will tell us the precise mass and spin of these hidden engines. We will no longer have to infer their presence from the glow of gas around them or the motion of nearby stars. We will feel their dance directly. Dr. Alberto Cesana, a leading theorist in this field, explains that this is akin to taking a galactic census by listening to its deepest vibrations. By detecting the hum of many such mergers across the cosmos, LISA will map out the population of supermassive black holes, revealing how common they are and how they have grown over cosmic time through successive mergers. Sophisticated computer simulations are already making predictions about this cosmic chorus. They model the complex dynamics of black hole pairs, accounting for the gravitational influence of stars and gas that can either hasten or stall their final plunge. These simulations predict a specific rate of mergers, a statistical hum that should fill the universe. When LISA turns on, the volume and character of this hum will be a direct test of our models of galaxy formation. A louder signal than expected would indicate a more violent merger history in the universe's past. A quieter one might suggest that black holes often stall in their orbits, never quite reaching that final, cataclysmic merger. This gravitational wave astronomy connects the largest scales of galactic collisions directly back to the quantum fluctuations from which all structure grew. The same primordial blueprint that dictated the distribution of galaxies also set the stage for every black hole merger that will ever occur. By listening to these echoes of cosmic violence, we are not just learning about black holes. We are testing the entire architectural plan, from the first whisper of inflation to the final, silent embrace of dark giants. The grand cosmic architecture might be woven from threads of spacetime itself, threads that are far from smooth. At scales a billion trillion times smaller than an atom, the very fabric of reality may dissolve into a seething, turbulent froth. This is the quantum foam, a concept pioneered by physicist John Wheeler, where the notions of here and there lose all meaning. In this frenetic sea, virtual particles and antiparticles perpetually wink in and out of existence, and microscopic wormholes tunnel through a chaotic foam-like structure. It is a realm where gravity and quantum mechanics collide, a domain so tiny we cannot yet probe it directly, yet its theoretical implications for the large-scale universe are staggering. The quantum foam suggests that spacetime is not a continuous stage upon which the cosmic drama plays out, but is itself a dynamic, granular participant. This leads to a profound question. Could the hidden patterns that dictate galactic growth be rooted in this microscopic chaos? The quest for a theory of quantum gravity seeks to answer this, with two leading candidates offering breathtaking visions. Loop quantum gravity proposes that space is not smooth, but is woven from a network of finite, one-dimensional loops. Imagine the fabric of the cosmos as an inconceivably fine mesh, with each tiny loop representing a discrete quantum of area. The properties of this spin network could determine how spacetime behaves on the largest scales, potentially imprinting subtle statistical signatures on the universe we observe. String theory, in contrast, suggests that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational modes of these strings give rise to all the forces and particles in nature, with gravity emerging naturally from the theory. To make the math work, string theory requires extra spatial dimensions beyond the three we experience, dimensions that are curled up into shapes known as Calabi-Yau manifolds. The specific geometry of these hidden dimensions would dictate the laws of physics in our visible universe, effectively setting the cosmic blueprint from the very beginning. These are not just abstract mathematical exercises. If spacetime is truly granular, it could leave a faint, fossilized imprint on the oldest light we can see. The relentless quantum fluctuations of the foam in the very first instance after the Big Bang could have been magnified by inflation, creating a specific, non-random pattern in the cosmic microwave background. Our most precise maps from the Planck satellite show a background that is overwhelmingly smooth and consistent. But some cosmologists are searching for tiny anomalies, subtle correlations or preferred directions that could be the ghostly signature of a granular spacetime. Furthermore, the initial distribution of those primordial density seeds, the very ones that grew into the cosmic web, might have been dictated by the statistical properties of this underlying quantum geometry. The great voids and filaments could be the macroscopic echo of spacetime's microscopic texture. This perspective forces a complete synthesis of everything we have explored. The dark matter halos, the spiraling density waves, the galactic mergers, and the vast cosmic web are not merely patterns imposed upon space. They are patterns emerging from space, from the deepest, most fundamental level of reality. The architects of infinity are not just external forces acting upon the cosmos. They are the cosmos, operating with the same set of rules from the Planck length to the galactic supercluster, weaving a single, unified tapestry across all scales of existence. These separate cosmic patterns are not isolated rules, but interlocking gears in a single, magnificent machine. The graceful spiral of a density wave is only possible because an unseen dark matter halo holds the galaxy together, its gravity preventing the disk from flying apart. That halo itself was sculpted by the primordial blueprint of the cosmic web, which channels fresh gas along its filaments, feeding the galaxy and allowing new stars to light up the spiral arms in the first place. And when star formation runs too hot, the resulting supernova, or the central black hole they sometimes feed, launch galactic winds. These winds blow material back out into the web, a self-regulating feedback loop that ensures the galaxy does not consume its fuel in one frantic burst. This intricate dance connects the very large to the very small. The quantum seeds of inflation, stretched to cosmic proportions, dictated the distribution of dark matter. The dark matter, in turn, defined the gravitational wells where ordinary matter could flow, collapse, and spin, igniting stars whose lives and deaths would then chemically enrich and energetically reshape their surroundings. It is a continuous cycle of construction and regulation, operating across billions of years and billions of light years. The stunning success of supercomputer simulations like Eagle and Illustris lies in their ability to weave these threads together. Cosmologists like Dr. Carlos Frank create virtual universes in silicon, programming in the known laws of physics, gravity, and hydrodynamics. They do not pre-draw the spiral arms or the cosmic web. They simply set the initial conditions based on the cosmic microwave background and let the simulation run. And from this digital Big Bang, the patterns emerge on their own. The simulations spontaneously generate dark matter halos, galaxies with the correct rotation curves, and a large-scale cosmic web that mirrors our own maps of the real universe. They even reproduce the Kennecutt-Schmidt Law, the observed relationship between gas density and star formation. This is the ultimate validation that we are not just listing separate facts, but uncovering a unified cosmic narrative. The universe, for all its apparent complexity, operates on a set of deeply interconnected principles. It is a system where the largest structures and the smallest processes are in constant, dynamic conversation, all following a score that was written in the first fleeting moments of time. This cosmic order, from the quantum whisper to the galactic supercluster, reveals a universe of breathtaking coherence. We have traced the hidden patterns, seeing how the faintest ripples in spacetime were amplified by dark matter's invisible hand, then painted with the light of stars through the precise mechanics of spiral density waves and galactic cannibalism. Every brilliant galaxy is a testament to this intricate dance, a dance choreographed by a blueprint written into the cosmos at its birth. These are not separate stories, but interconnected chapters of a single grand narrative. This understanding does more than illuminate the past. It grants us a predictive power, allowing us to forecast the future evolution of these structures toward their quiet, dark energy-dominated end. With every new map from powerful telescopes and every subtle signal from gravitational wave observatories still on the horizon, we refine this cosmic blueprint. We are not just cataloging the universe, we are learning to read its original source code, moving ever closer to the ultimate architects, whether they are the fundamental laws of a quantum reality, the statistical chance of a multiverse, or a deeper truth waiting just beyond our current grasp. The mystery of why these particular patterns exist at all remains one of the greatest enigmas. What do you believe is the ultimate source of this cosmic order? Share your thoughts in the comments. and subscribe for more journeys into the heart of space's deepest questions.